In this presentation, I'll be explaining what is an instrumentation amplifier, where it is used, and what is the equation for the gain of the instrumentation amplifier. We'll be deriving that equation, and as well as one of the application of instrumentation amplifier. Continuing, instrumentation amplifier. In a number of industrial and consumer applications, it is required to measure and control physical parameters such as temperature, humidity, light intensity, water flow, etc. These physical quantities to be measured. And these physical quantities that are measured with the help of transducers. We'll be measuring these physical quantities like temperature, humidity, light intensity, water flow, etc. using the devices what is called transducers. And this output of these transducers had to be amplified because that magnitude would be very low, maybe in the range of millivolt. That is to be amplified so that it can drive the indicator or display system. And this function is performed by the instrumentation amplifier. Now, the output of the transducers, which converts this physical quantity into electrical quantity, that magnitude will be very small. And these quantities or this magnitude of these voltages are to be amplified using instrumentation amplifier. The important features of instrumentation amplifiers are, first feature is it should have a high gain accuracy, and high common mode rejection ratio, high stability with low temperature coefficient. It should be very stable device. I mean, that amplifier should be stable. It should not change with respect to the as the temperature changes. Low DC offset, low output impedance. These are the important features of an instrumentation amplifier. And commercially available instrumentation amplifiers are, there are certain that is analog device instrumentation amplifier by AD521, AD524, AD620, AD624. These are all analog devices. This is a manufacturer's name. That is the instrumentation. Like National Semiconductor is also producing this. That is LM series, LM363 XS, or XS can be either 100, 100 or 500. Like that, National Semiconductors are producing this instrumentation amplifiers. And Burbron, that is producing, that is IN101, 104, 3626, 3629, like these are Burbron products. Therefore, these are the commercially available instrumentation amplifier, and these are the important features of instrumentation amplifier. Anyway, instrumentation amplifiers are used to amplify the electrical signal available at the output of the transducer, which measures the physical quantity like temperature, humidity, light intensity, water flow, etc. etc. Continuing the instrumentation amplifier, one of the main heart of this one instrumentation amplifier is the differential amplifier. This is shown a differential amplifier, and in this one we have already seen this differential amplifier, and we have derived also in the previous presentations. And here the inputs are V1 and V2 are the inputs too. And here the resistances are marked as R1 and R1 and R2. This is R1 and this is R2. And similarly R3 and R4. These are the resistance, and this op-amp is connected. Output is, this is a circuit diagram of a differential amplifier in which the input signals are V1 and V2 and output is equal to V0. Output is a function of the input voltage, input difference in voltage. And now let us analyze this one. Now, since we have two inputs here, the output corresponding to two inputs can be obtained by using the superposition theorem. That is, when V1 is present, V2 will be grounded. What is the output? That is called V01. Similarly, when V2 is present, V1 will be grounded, and corresponding the output will be V02. When V1 and V2 are present, then the output will be V0 will become V01 plus V02. That is the superposition theorem. Based on that one, we'll be finding out what is the output voltage when two inputs V1 and V2 are applied at the input of a differential amplifier. Coming to this one, V0 equal to V01 plus V02, but V01 corresponding to when V1 is alone is present, V2 is grounded, and V02 is the case when V2 is present and V1 is grounded. What is the corresponding output? That is V0. Now let us see the V01. That is when V1 is present and V2 is grounded. What is the output? That is called V01. That is when this is grounded and this is present. For when V2 is present, you can see that when the voltage at this point is given by sorry, this when V1 is present, V2 is grounded, V1 is present, the voltage at this point is given by V1 divided by, this is R3 plus R4 into R4. That is the total R3 plus R4 into R4. That is uh, uh, V, we setting V1 divided by R3 plus R4 into R4 divided by R3 plus R4. That is the voltage at this point. We'll be getting this is the voltage. And then it is a non-inverting amplifier. Output equal, this is the input that is coming, this one. And the output will become whatever that voltage, that is V3 divided by R3 plus, sorry, V1 divided by R3 plus R4 into R4. That's voltage, that into 1 plus R2 by R1. 1 plus R2 by R1. That is the non-inverting amplifier equation. Whatever the voltage coming here, that into 1 plus R2 by R1, it is the output voltage. Therefore, because this is grounded, therefore say non-inverting amplifier, the gain equation equal to 1 plus R2 by R1, whatever the input voltage here, that voltage equal to V1 divided by R3 plus R4 into R4. And substituting here, and you'll be getting V01 equal to V01 equal to here, you can get corresponding equation V1 into R2 by R3 into 1 plus R2 by R1. And this is the equation for V01. And what is V02 here? V02 means when V2 is present, V1 is grounded. When V1 is grounded, of course, this is also ground potential. Then when V2 is present, output voltage is just like an inverting amplifier. And V02 equal to minus R2 by R1 into V2. Minus R2 by R1 into V2. Therefore, this is equal to V01 when V1 alone present. And this is equal to V02 when V2 alone present. This is, of course, working as a non-inverting amplifier. In this case, it is working as an inverting amplifier. Therefore, when both inputs are V1 and V2 are present, output equal to V01 plus V02. And that we are, V0 equal to V01 plus V02. That is, we are V1 R4 divided by R3 plus R4 into 1 plus R2 by R1 minus R2 by R1 into V1. And reducing this equation, we will be getting it is equal to minus R2 by R1 into V1 minus R4 divided by R3 plus R4 into V1. That is equal to minus R. Here this is equal to R2 by R1 into R4 divided by R3 plus R4 into V1. Or we are reducing this one and applying this after reducing this equation here, and then you will be getting that it is equal to minus R2 by R1 into V2 minus 1 by R3 by R4 plus 1 into V1 into R1 by R2 plus 1. Or if R1 by R2 equal to R3 by R4, if R1 by R2 equal to R3 by R4, and substituting that equation here, this output voltage of this output voltage is equal to, which is equal to R2 by R1 into V1 minus V2. So the output voltage is equal to R2 by R1 into V1 minus V2, provided this we'll be getting it is equal to R2 by R1 equal to it is equal to will be R1 by R2 equal to R3 by R4. In that case, the output voltage equal to, we'll be getting it is equal to R2 by R1 into V1 minus V2. That is the output voltage here when both inputs are present. Therefore, output voltage when only V1 is present, that is when V2 is grounded, V01. When output voltage when V2 is present, that is V1 is grounded, it is equal to V02. Then output voltage when both inputs are present, it is the sum of this one, V01 plus V02. That is the superposition theorem. Applying that one, we'll be getting the output voltage is equal to R2 by R1 into V1 minus V2, provided R1 by R2 equal to R3 by R4. This is called a differential amplifier. Now, this is the circuit diagram of an instrumentation amplifier. Therefore, it consists 3 operation amplifier. two op-amp at the inputs front end side, input side, and one op-amp at the output side. And the front end op-amps here we are giving the inputs to the, for example, in this case, we are giving the input to the top non-inverting terminal to the V1 and to the bottom non-inverting terminal to the V2. For V1 is given plus here and V2 is given plus here. And this is arranged in this fashion here. Feedback resistance of the first equal to say R1 and here also R1. And there's actually a variable resistance normally. It's RG, gain adjustment resistance equal to RG is the, so the two op-amps are connected like this one. And here a voltage of V1 dash is available and here a voltage of V2 dash is available. And then same as what we are discussing in the previous slide, here V1 dash is the, here V2 dash is the, what is the output provided this ratio, that is here, we are seeing that this is equal to R2 is equal to R3, R3 by R2, and this is also R2 by, R2 and R3 by R2, both are equal. Then the output voltage is, as we have done in the previous case, we'll be getting, it is equal to the difference in voltage of V1 dash minus V2 dash into this ratio, that is this R3 by R2. That is already we have derived that equation in the previous slide corresponding to this one. Now we have to find out what is V1 dash and what is V2 dash looking at the input side. At the input side there are two voltages like V1 and V2, and we can apply the superposition theorem. First assume that V1 is present, then you ground V2 and you find out what is the corresponding voltage V1 dash. Then again V2 is present and V1 is grounded. Then see what the sum of that one will be getting V1 dash. Okay, similarly V2 dash also we can get. Let us see first V1 dash, we can say that. Okay, we coming to that one, V1 dash is equal to, first we are assuming that V1 is present and V2 is grounded. This is grounded and V1 is present. Since this is grounded, this is a ground potential because virtual ground, and therefore this is the ground potential. So this is grounded and you are applying the input to the non-inverting terminal, and this is grounded, it is a non-inverting amplifier. Therefore gain is given by 1 plus R1 by RG, 1 plus R1 by RG into V1, 1 plus R1 by RG into V1. That is the output when V1 is present. When V2 is present, same argument, V1 is grounded. When V2 is present, we can say that one, V2 will be available here, and because the virtual ground, then V2 is coming here, and this is it is a inverting amplifier, and this is grounded. This is an inverting amplifier. Gain equal to minus R1 by RG. Therefore, corresponding output equal to minus R1 by RG into V2, but V2 is present. Therefore, when both V1 and V2 are present, this is the output voltage V1 dash here. The same argument, you can find out what is V2 dash. When V1 is present, you find out what is the voltage. When V2 is present, what is the voltage? Sum of that one will be V2 dash. Assume that first V2 is present here. When V2 is present, you are applying to a non-inverting terminal, and this is grounded because V2 is present, this is grounded. Therefore, this is a ground potential, or this is a ground potential. Then it is a non-inverting amplifier. Then output is corresponding to here, that one equal to 1 plus R1 by RG into V2. 1 plus R1 by RG into V2. Then second case, when V1 is present, V2 is grounded. When V1 is present, you will be getting V1 here, and this is grounded. Therefore, the output is equal to minus R1 by RG into V1. Minus R1 by RG into V1. Therefore, here reducing that one, you are getting what is the equation for V1 dash. From this equation, you are getting what is V1 dash. Similarly, from this equation, you are getting what is V2 dash. That is V1 dash and V2 dash is found out applying the superposition theorem. And then once you get V1 dash and V2 dash, as I told you, the output voltage is a differential amplifier that is equal to the difference in this voltages V1 dash minus V2 dash into this feedback resistance R3 by R2. That's all, R3 by R2. So for the substituting the equation 1 and 2 in the third equation, the equation is equal to output equal to V1 dash minus this one, V1 dash minus V2 dash into the feedback resistance R3 divided by R2. We have to substitute this V1 dash from this equation 1 and V2 dash from the equation 2, and you can get what is the corresponding the voltage, output voltage V0 available. That is, you are substituting that one here, and then you'll be getting it is equal to output voltage equal to R3 by R2 into V1 minus V2 plus R1 by RG into V1 minus V2 okay minus V2 plus V1 or twice V1 minus twice V2, and then we'll be getting the corresponding output voltage is equal to here R3 by R2 into V1 minus V2 into 1 plus 2 times R1 by RG. Therefore, this is the output voltage, and we are taking V1 minus V2 outside, then we'll be getting it is equal to the R here R3 by R2 into 1 plus twice R1 by RG. That is R3 by R2 into 1 plus twice R1 by RG, and this is totally it's a gain that into the difference in voltage V1 minus V2, that V1 minus, or we are amplifying this difference in voltage with a gain of this much R3 by R2 into 1 plus twice R1 by RG. Therefore, that this part is we call it as the gain of the instrumentation amplifier, that is represented as capital G, which is equal to R3 by R2 into 1 plus twice R1 by RG. Therefore, this is the gain of the instrumentation amplifier. For an instrumentation amplifier, there will be 3 op-amp. They are connected in this fashion, and you will be getting the output voltage which is proportional to the difference in voltage V1 minus V2, of course with a magnitude change or gain that is given by the ratio R3 by R2 into 1 plus twice R1 by RG. Therefore, this is the gain of the instrumentation amplifier that will be amplifying the difference in input signal V1 minus V2. We have seen we had derived equation for the instrumentation amplifier gain, and it is equal to R3 by R2 into 1 plus twice R1 by RG. This is the gain of the instrumentation amplifier, and this instrumentation amplifier can be used certain different application like amplifying the low magnitude of signal available at the output of the transducer. As an example here, in a resistive transducer, resistance changes as a function of the physical quantity to be measured, like temperature. If you are considering a resistant temperature detector, RTD, which is a resistant temperature which is varying as temperature changes, the resistance value changes. Therefore, if you consider a Wheatson's bridge here, as temperature changes, this arm resistance changes. Initially assume that it's in a balanced condition. As the temperature changes, this resistance changes, and that will be going unbalanced, and then there will be a voltage that is available at the output of the bridge, and this signal, this voltage is that is given to a that is a op-amp instrumentation amplifier. This is the instrumentation amplifier what we have already discussed. This voltage is amplified, and that is given to an indicator or a display device. That is the block diagram of an application of instrumentation amplifier. Now coming to that one, bridge is initially balanced. Initially the bridge is balanced by the supply voltage VDC. By the supply voltage VDC, this is initially balanced. Now as temperature changes, the resistance RT, R capital, the resistance RT or the resistance of the transducer, that will be changing, causing an unbalancing. Therefore, there will be unbalancing in the bridge, so that a voltage will be coming across this and in the bridge, and the bridge will be getting unbalanced because these two voltages will not be equal. This voltage will not be equal to this voltage, and there will be a difference in voltage that is available, which is given to the input of a this instrumentation amplifier, and the differential voltage now gets amplified by the differential instrumentation amplifier. Instrumentation amplifier, as I already explained, there will be a 2 op-amps at the input side, and there will be 1 op-amp, so differential amplifier at the output side. So for 3 op-amp instrumentation amplifier, and here as we are seeing, the output voltage available of this one is equal to the difference in voltage of this one into the gain of this instrumentation amplifier, which is equal to R3 by R2 into 1 plus, of course, R1 by RG. This is the gain of the instrumentation amplifier. For an IC, analog IC on AD620, gain of amplifier G is given by this one, and it is example, it is given what is this values of this, or this resistance values are given, all are at 25 kilo ohms, and this RG is given as it is equal to 50 ohms, and based on that one you can calculate the gain of this amplifier. That will be getting, it is equal to 1001, that is equal to 1001 amp gain of the amplifier is getting. Therefore, the very small value of the voltage that is available at the output of this bridge can be amplified using an instrumentation amplifier. That will be amplified the difference in voltage. Therefore, this is one of the application of an instrumentation amplifier, which is used to amplify the signal that is available at the output of the bridge. And one of the bridge amp is the transducer. Normally, to as an example here, temperature sensor, maybe the resistant temperature detector. So this is one of the application of an instrumentation amplifier, which amplifies very small voltages, which can be used either to display or control the device.